So last time we met, we were talking about inverses. And we had talked about the procedure for finding inverses that were for functions that were represented with an equation. And we looked at two examples of kind of doing that. I'd like to continue and do a few more examples where to review some of the algebra techniques from last year that I think are, relevant and maybe not at the forefront of our memory. So they're just, again, useful things to kind of remind ourselves about. So let's say we have the function p of x equals 3x squared minus 4. So remind me again, what do I do to find the inverse? Yeah, so we'll replace that p of x with a y equals, and then we'll get the x by itself, and then swap the x and y variables. If I'm to solve this for x, what should I do as my first step? Add 4, very good. And then next I should? Yeah, I agree with that. And then I should square root both sides, okay? So I'd write it like this then, right? No. What's wrong with what I've written here? What was that, Mark? No. That's it, Kayla. The plus or minus. Remember, when I square root both sides of an equation, it generates a plus or minus. Good catch. Now it's correct. So there was nothing wrong with the way I took the square root of both sides other than omitting that plus or minus, which sounds like had we not mentioned that, it would have been one that the majority of us might have forgotten to do too. Consider this your reminder that when you square root both sides of an equation, we generate a plus or minus. And then now that the x has been isolated, we can swap the x and y's. So I would say that p inverse of x is plus or minus the square root of x plus 4 over 3. What can I say about p inverse of x? If you look at that, what can we say about p inverse of x? What was that? Somebody whispered it, I thought I heard. Yeah, that's correct. When you say it aloud so you can get credit for it, right? Yeah, so why is this not a function? Yeah, mainly the plus or minus is the thing that's indicating to us that this is not a function. Now, it's very likely that, like this is kind of a crummy outcome, right? We'd like to be able to take that any function and create an inverse for it that is still a function. And there's kind of a way to do that, that being restricting the domain for the original function. So if, let's say, in addition to p of x equals 3x squared minus 4, we're told that x is also greater than or equal to 0. So here what we've done is we've restricted the domain. You guys might remember from your Algebra 3/4 class last year talking about this. Now, nothing really happens differently until we get to this step here. If I know that x is greater than or equal to 0, what that ostensibly does is it gets rid of the minus from the plus or minus, which would make p inverse of x a function. And this is a trick that we'll use again later this semester when we look at inverse trig functions, is that if we have a situation where the inverse will not be a function, what we'll do is some tricky domain restriction in order to create something, an inverse, that is still a function that we can use on our calculator. Everybody okay with that idea? All right. Let's do another. So let's say we have f of x equals the square root of 12x plus 5. So if, again, we're looking for the inverse, we had said earlier that you rewrite the function notation using y equals notation. And we solve for x and then swap the x and y variables. What's the first thing I would want to do to solve for x here? Square both sides. Good. Oops. Okay. And then I would? Good. And lastly, I would divide by 12. And now we can swap the x and y's. So I'd say in this case f inverse of x is x squared minus 5 over 12. Does anybody see anything fishy with this? Yeah. This is still a function. Let's see what happens if I try doing f inverse of x of negative 2. So I get negative 1/12. So what this tells me is the point negative 2, negative 1/12 is a member of f inverse, right? What does that tell me about f? Negative 1/12, comma, negative 2 should be a member of f. Does that make sense? If I go back and look at f, should I be able to get a negative y value from f? No, right? So there's a little bit of a domain issue going on here where we need some kind of restriction going on in one of these two places, either in the function or the inverse, for that to really match up. So there's a little bit more going on here than meets the eye. For right now, I don't need you to do anything with that. If you go ahead and tell me that this is the inverse, that's fantastic. I'm just pointing these things out because later on when we talk about trigonometric inverses and some of the hoops we have to jump through in order to construct these things so that they work appropriately, I'm going to go back and kind of touch on these same kind of issues that we're seeing here, and as justification for some of the hoops that we have to jump through when we build those trigonometric inverses. So again, all these things that I've done here talking about restricted domains and this function issue, or this inverse issue on this example are not things I'd expect you to be able to repeat. I'm just kind of showing them to you because I'm going to reference having to deal with some of these issues and doing some of these kind of tricks a little bit later. And I want to present these ideas now in something that was a little bit more familiar of a setting. Is that okay? Let's do another. Let's say we have g of x equals 1/2 times 3 to the 4x. So, just like usual, we'll replace the function notation with y equals notation. And then we'll try to solve for x. What is the first thing I should do to solve for x? Multiply by 2 to both sides, right? Or same thing as dividing by 1/2. Multiplying by 2 is a little bit neater, sounding to me anyways, rather than dividing by a fraction, but you're doing the same action, so either way of phrasing it is fine. Yeah, so Miguel says we need to take the log here of both sides to cancel out the exponential. Which logarithm should I use? Log base 3. I want the base of my logarithm to match the base of my exponential. Now, is it necessary I do that? No, really, any logarithm will work, but the algebra is much, 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 much neater if I just use log base 3 in this case rather than like log base 10. But there's nothing wrong with using log base 10. It just makes the problem a little bit more difficult than it needs to be. And since I am not about making my life more difficult, I will do log base 3 to both sides. And then my last step would be to divide by 4. Now the convention when we do that is we would probably write this as 1/4 times the logarithm, rather than writing that as like log base 3 of 2y all over 4. Not that that's incorrect, but it's just kind of not really the standard way we write things. I wouldn't mark it wrong if that's the way you wrote it, certainly. But I find it unlikely that like on a multiple choice standardized test, the answer would be represented in that way. More likely it would be written the way that we've written it here. So my last step then is to swap my x and y variables so I can say that g inverse is 1/4 log base 3 of 2x. And here there's no domain or range issues, so like this inverse works exactly as we hope it would. Let's do one final example. What letter am I on? Is it B? The alphabet is hard, guys. You know, you got all those letters and stuff. You know, like the alphabet. That's good, because I was talking to the alphabet the other day. It doesn't like you. No. No. Just mostly gossip about you. The letter U, obviously. Right? More alphabet jokes. That is LN is what that symbol is there. So, again, the way I write my logs on the sheet of paper is I use script, so I kind of write them cursive, so that I don't accidentally mistake my LOG for like a 10G, or my LN as a 1N, which is very easy to do if you're just looking at something quickly and not thinking about what it really is. So I like to write my logs in cursive so that I don't make that mistake when I look at it later. That's just me personally. You can do whatever you like, but when I'm writing them on the board, I'll always use kind of script LOG or LN to do that. Okay, same plan. We'll rewrite using the y equals notation. And then to solve for x, what's the first thing I'd want to do here? Multiply by 3/5. That sounds good to me. And you could write that as 3/5 y or 3y over 5. Either is fine. Because I know where I'm going here. I'm going to choose to write it this way because I think it makes life a little bit neater, but it's not really a big deal. What should I do next? Am I going to get rid of that ln? Remind me again, what does ln mean? Yeah, and what does that mean? It's log base e, right? I've heard some people saying e there. Okay. So what am I going to need to do to both sides to cancel out that natural log or that log base e? We're going to use the exponent base of e to both sides. I like to say big E. So I'll write it. I always write it with like an exaggerated size, so I don't accidentally mistake myself multiplying both sides by e. E is the base of an exponential, so my equation becomes the exponent, and e is the base for that exponential. Is everybody okay with what we've done there? Okay. We'll add 1 and divide by 7. And then swap our x and y variables. Whoa. That sounds scary. It's not even Halloween. It is spooky. Okay. And again, on this one, there's no issues with this inverse. It works as we'd expect it to. There's no issues with the domains going on here, which is nice. That wraps up section 7. Today we'll talk about the last section in chapter 1. Yeah. Correct, not tomorrow. Of course, Val. So, stop talking, please, guys? Thank you. So in section 8, we're going to be talking about graphical transformations. So what I want you to remember here is this idea from your Algebra 3-4 class about families of functions and parent functions. So every member of a family of functions can be written as a transformation of the parent function we'll call that parent function f of x, where y equals a times f of 1 over c x minus h plus k is the general form for every member of that family of functions. And what these coefficients tell us, these a, c, h, and k, describe the physical transformations that are going to be occurring. That's okay. Maybe he's just a big fan of the Joker. You know, that movie's coming out soon. I think Joaquin Phoenix is already a little kind of on the crazy side. Uh-oh. V is just short for vertical, and H was just short for horizontal. I'll read these aloud here in just a moment. because I know that my penmanship leaves something to be desired. So I apologize for all of that in advance. That's a lot of writing. I'm sorry, what? Are you talking to me or to yourself? A half, a third, 0.1. So, Rule 1 says if C is less than 0, we're going to reflect over the y-axis. If the absolute value of C is not 1, either the absolute value of C has to be greater than 1, in which case it's a horizontal stretch by a factor of C, or the absolute value of C would have to be less than 1. In that case, it would be a horizontal shrink by a factor of C. If the A value is negative, we have a reflection over the x-axis. And if the absolute value of A is not equal to 1, either the absolute value of A is greater than 1, in which case it's a vertical stretch by a factor of A, or the absolute value of A would be less than 1. In that case, it would be a vertical shrink by a factor of A. If the absolute value of H is non-zero, then either H has to be less than 0, in which case we go left H units, or it would have to be greater than 0, in which case you'd go right H units. Lastly, if the absolute value of K is non-zero, either K has to be less than 0, in which case you'd go shift down K units, or it'd have to be greater than 0, in which case you'd shift up K units. Hopefully this looks at least somewhat familiar from last year, this set of criterion. Now, in most cases last year we didn't have this 1 over C part. Mostly we just talked about A, H's, and K's, because for the majority of the functions we studied last year, a vertical stretch and a horizontal stretch were kind of equivalent. So consider like an absolute value function. If I stretch horizontally, is the same thing as compressing vertically because of the symmetry at the origin. Similar thing happens with quadratic functions. So a lot of the time in Algebra 3-4 we don't talk about this 1 over C piece. It'll certainly be important in trigonometry when we start graphing sine, cosine, tangent, etc. So we're certainly going to talk about that here. Are these rules things that you should have memorized? Yes. You do need to know these rules, for sure. And to give you an example of the kind of thing I'd expect you to be able to do with these, let's do some examples. So one of the things I'd ask you to do would be to describe the transformation. So let's say we have g of x equals 2 times f of x plus 1 plus 4. The first thing I'm going to do is identify the values for a, c, h, and k. What is my value for A? 2. What's my value for C? 1. Remember here we have C is being multiplied. So for A's and C's that are being multiplied, if you don't see the A or C, they must be 1, because 1 times anything stays the same. For H's and K's, if you don't see them, they would be 0, because they're being added and subtracting, and if you add or subtract 0, that stays the same. The H is -1, very good, and K is 4. So I'm just going to go then list the numbers 1, 2, 3, 4, 5, 6 that correspond to the 6 rules that we just wrote down above. So rule 1, what I need to check is the sign of A. In this case, we notice that A is not less than 0. Everybody agree with that? So nothing happens for 1. I'm just going to put a dash there to indicate that I looked at it, but there's none of this transformation doesn't really apply. 2, we look at, is the absolute value of A equal to 0? Well, no. The absolute value of 2 is 2. And so the next thing we need to do is look at, is 2 greater than 1 or less than 1? Well, clearly that's greater than 1. So if I look at my list, I have a vertical stretch by a factor of 2. Everybody okay there? Oh my goodness. Why am I doing A's? What comes first? C's. How come nobody yelled at me before to be like, you're going out of order, Mr. Kulik? If you see me making mistakes, don't sit on that. Go ahead and interrupt, please. Okay. Yeah, all right. Sure, Bob Ross. All right. So 1, we're looking at whether C is positive or negative. In this case, I see C is positive, so nothing happens for 1. 2, I'm checking, is the absolute value of C equal to 1? In this case, it is, so nothing happens for 2. In 3, we're looking at the sign of A. We see that A is positive, so nothing happens for 3. In 4, we're looking at the magnitude of A, so we notice the absolute value of A is not equal to 1. Since it's greater than 1, we have a vertical stretch by a factor of 2. Excuse me. Back on track now, right? My apologies for going out of order there, but at least I realized what I was doing before we got too far, right? JJ. Of course. For 5, we're looking at our H's. Here I notice that my H is not equal to 0. And since the H is less than 0, I know I'm going to be going left. And the last one is about K, in which case, what's going on with K? Up 4. Any questions about this one here? Let's do one more example, and then we'll continue on. Stop. So let's say g of x equals -3 times f of x of 2x minus 4 and then minus 2. Just like we did before, we'll start by listing our values for a, c, h, and k. So what's our value for a? -3. What's our value for c? 1/2. So recall that we're looking at this is our general form. So if I factor out the 2, I have that 1 over c is equal to 2. So c would be the reciprocal of 2, which is 1/2. I heard many people say 1/2, but I've also heard some of us say 2. Also, I want to make sure I explain why it's 1/2. Everybody okay with that idea? Okay. In general, the rule is that c is always like the reciprocal of the coefficient on x, if that helps. Our value for h here is 2. We had to make sure we factor so the coefficient on x is 1. That's sneaky there. Don't be tricked by the sneaky things. And then lastly, our value for k is -2. So again, I'll write my list 1, 2, 3, 4, 5, 6. In step 1, we look at the sign of c. Since c is positive, there's no reflection. In step 2, we look at the magnitude of c. Since the absolute value of c is less than 1, we have a horizontal shrink by a factor of 1/2. On step 3, we look at the sign of a. Since the sign of a is negative, we have a reflection across the x-axis. In step 4, we look at the magnitude of a. Since the magnitude of a is greater than 1, we have a vertical stretch by a factor of 3. In step 5, we look at h. Since the h is positive, we're going to go right. And since the magnitude of a is 2, we're going to go right 2 units. And in step 6, we look at the k. Since the k is non-zero, or since the k is negative, we're going to go left. And since the magnitude of k is 2, we're going to go left 2. Yes. Thank you. That's what I like to hear. As soon as I make those mistakes, jump all over me. Thank you. I meant down, of course, 2 units. Everybody feel comfortable doing this? So, why did I choose the order I chose to list these rules for these transformations? Because if we're actually performing the transformation to a parent function step by step by step, this is the order in which I'd want to do each of these transformations separately. First, I'd want to do any reflection across the x, and then any horizontal stretch or shrink. Then do the vertical flip, and any vertical stretches or shrinks. Then move left or right, and then move up or down. I'd want to do that specifically in that order, because those transformations are not necessarily commutative. If I shift left or right and then do a vertical stretch or shrink, it may not be the same thing as going stretching and shrinking and then moving left or right. So we have to be a little bit careful about the order that we apply these transformations. And that's why I've written them specifically in that order, where we're going to do the stuff for C first, and then A, and then H, and then K. So the order there does matter. Is everybody okay with that idea? Okay. How are we doing time-wise? We still got some time, right? Or would you rather just like finish 5 minutes early? I mean, like, I understand, like, it's a long time to be doing math. So let's say that this is the graph of y equals f of x. And what I want to do is graph y equals 2 times f of x plus 3 minus 1. So I'm going to start the same way I did as the previous. I'm going to list my 6 possible transformations here. Since c is 1, there's nothing to do for 1 and 2. Since a is positive, there's nothing to do for 3. Since a is, or the magnitude of a is greater than 1, we'll have a vertical stretch by a factor of 2. Since the h is negative 3, we're going to go left 3 units. And since the k is negative 1, we're going to go down 1 unit. See, no mistake this time. Everybody okay there? So I'm going to graph like this in 3 stages. So I'm going to start with 4. I'm going to draw that graph in blue. And then I'm going to perform step 5 to the blue graph. I'll draw that graph in purple. And then I'll do step 6 to the purple graph, and I'll draw that graph in orange. Is everybody okay with that plan? So if I'm doing a vertical stretch by a factor of 2, what do I need to do to these coordinates to perform that transformation? Multiply the y's by 2. So the point negative 2, 0 stays the same. The point 0, negative 4 becomes 0, 0, negative 2 becomes 0, negative 4. 2, 0 stays the same. And then 4, 4 becomes 4, 8. Everybody okay with that idea? So far, so good? Now I'm going to do the transformation 5. To go left to 3 units, what do I need to change? Good. I need to subtract 3 from each x coordinate. So this one becomes negative 5, 0. This one becomes negative 3, negative 4. This one becomes negative 1, 0. And this one becomes 1, 8. And then to do the down one, what would I need to do? Good, subtract 1 from the y's. So this becomes negative 5, negative 1. This one becomes -3, -5. This one becomes -1, -1. And this one becomes 1, 7. And what I have is like this terribly messy graph. My apologies. Hopefully the color coding at least feels okay there. Does everybody feel okay with doing this? So you can do this step by step, or alternatively, what can we do here? We can try to do this all in one fell swoop. So if I do this, for example, for the point -2, 0, let's actually do that. That is going to become 1 times -2 plus -3. And then I'll have 2 times 0 plus -1, which gives me the point -5, -1, which is the final location of that first point. If I do the same for -2, 0, I get 1 times 0 plus -3, 2 times -2 plus -1, which gives me -3, -5, which is the ending result for that middle point. And I can continue doing this, etc., etc. But this is a way to do the transformations kind of all at once, rather than one at a time. And I'm showing you this in particular because it helps justify the order in which we need to do the transformations. So if I do the order of operations, the first things I do are multiplication, right? So the first two things that need to be addressed are the C and the A. After multiplication, the order of operation is addition and subtraction. So that's why the last two things to address are the H and the K. And I've ordered the C before the A because the X's come before the Y's in a coordinate pair. And we ordered the H's before the K's because the H comes, or because the X comes before the Y in the ordered pair. So in terms of remembering the order for these transformations, it's right here, right? How do you guys feel about this transformations piece? You feel okay being able to write the transformations? Obviously, you might need to do a little bit of memorizing for those rules. This piece right here that I wrote down would also be worth your time memorizing. That little generic transformation is going to prove to be pretty useful, especially going forward. When we talk about graphing trigonometric functions. This is the technique we're going to use to graph them, is we're going to have some key features to the parent function and just transform those key features based on our values for A, C, H, and K to be able to generate the graphs a little bit more quickly. Okay.